All right, well, welcome to class 11 of Programming Tools CSE 224. Today we're going to talk about functions in C. We talked a little about functions in Bash in a previous lecture. And you should be familiar with the idea of functions in C. You've written these in CSE 121, for example. But I want to kind of go through the whole sort of start to finish idea of a function in C, how we declare them, how we use them, how we return values, pass values, and also the idea of function prototyping. And then look at some of the more perhaps unusual ways of passing information to a function, meaning, passing pointers. So when we talked about functions in Bash, I talked about modularizing code, right? Breaking a problem into smaller sub-problems, and that's what we're doing with functions, right? So for example, let's say you're writing a program that's doing some kind of cryptography or something, and it needs to generate a set of prime numbers, right? Well, generating prime numbers could be easy, could be difficult, not sure, right? But here's what you can be sure. If you have a function which can tell you whether or not a number is prime, then generating primes is easy, right? Just start taking consecutive numbers and pass it to your function and say, is this prime? How about this? How about this? And when the function comes back and says, yes, that's prime, hey, you've got a prime number, right? So rather than writing one program that tries to generate all the primes between, say, 2 and 1,000, I would first write a function that tests one number to see if it's prime, and then I would just call that in another program which loops from 2 to 1,000 for each number, calls the function. If the function says it's prime, I'll print it out, right? So this is the whole idea of modularizing your code, breaking your problem into smaller problems and tackling those smaller problems. And tackling a smaller problem usually means writing a function, right? And that function itself might involve writing other functions. We do this all the time. For example, when we write a piece of C code that wants to print something out, we call the print function, right? Printf. When we want to do input, we call the fgets function. When we want to calculate the square root of a number, we call the square root function. And we don't write those functions ourselves. Those are available for us, so that if we're trying to solve a quadratic equation, right, we just have to do negative b plus the square root of b squared minus 4ac divided by 2a. We don't have to write the square root part, right? So we're trying to break our problem down into smaller pieces. So what does a function look like in C? We can do something like this. So I could say let's make a function that I don't know. Let's just make a function that multiplies a number by 2. So I could say this is going to be a function that returns an integer, and it's going to be multiply by 2. All right. So let's just look at what we've got here, right? I've got a name. This could be more or less any name that I pick for the function. I'm making a function called multiply by 2. And there's two things we have to define along with the name of the function. We have to say what kind of arguments we're giving this function and what kind of value this function is returning. So I'm saying multiply by 2 will take a single argument, a single number we're passing to it, which will be an int, and I'm just calling it arg. I could call it anything I want. It's just a variable name. And this function should return a single integer. And I can do, whatever I want inside the body of this function. And eventually I need a return statement which says return something. And that something that I return here, that becomes the value of the function, the thing that this function is equal to. So now I can do something like this. Let's say I equals 5. And let's make j an integer, and let's say j equals multiply by 2i. And then let's print the values of I and j. All right. So I'm going to set I equal to 5. I'm going to declare to j to be an integer. I'm going to call multiply by 2, pass it this variable I. The result of that I'm going to save in j, and we'll print those out over here. So I'm using two windows here, right? I'm logged into the server twice, and I'm going to use this window to do my compilation and execution. I'm going to leave my editor window open. So I can say main, and it tells me I equals 5, j equals 10. And if I had said, you know, I equals 101, I can compile this and run it. It tells me I equals 101, j equals 202. Right? So this is an example of a function that takes an argument and returns an integer. And I could return, you know, anything that I wanted. I could choose not to return anything at all, so I could make this function void. And this is what our main program is. It's actually a function. It's a function named main. It's not taking any arguments, although sometimes it takes what argc and argv, right? And it doesn't return anything, which is why I don't have a return statement at the end of main. That's all there is to a function. It's a set of statements that will be executed when we access the name of that function. So this is called calling the function, and when we call the function, we pass 0 or more arguments to it by putting them in parentheses, separating them by commas. And inside this function, arg will take on whatever value this I was. And then when we say return something, this expression where we're calling the function is basically equal to whatever value was being returned. And so when I say j equals multiply by 2, j is equal to whatever this expression turned out to be. All right, so that's the basic framework for functions, mostly review for many of you. So, you know, I can call this argument whatever I want. I can call it hello if I want. It's just a variable, right? It makes no difference whether it's called arg or hello or x, and it certainly does not need to be the same thing as what I'm using when I call the function, right? And sometimes, you know, if there's something like, you know, student name that I might be passing here, I might call my argument student name, but that's just coincidence, right? You can call these things whatever you want. Arg is a pretty non-descriptive term for argument, but, you know, that's what I'm going to call it for now. All right, so something to keep in mind is this notion of pass by value. And we talk about this a lot. And here's what pass by value means. My main program is calling multiply by 2, and it's passing this variable I. When it makes a call to this function, when the CPU does what it has to do to start executing these statements, the first thing it does is it looks at the current value of I, which is 101, and that's what it actually passes to this function. It doesn't pass the letter I. It doesn't pass any information about I other than its value. Right? That's what pass by value means. It means when we send an argument to a function, the only thing the function gets is the value of the argument. And so, for example, I could do something like this. I could say arg equals arg plus 1. So add 1 to the value of arg and then return arg times 2. And when I run that, you know, we can see that arg was 101. This statement added 1 to it to make it 102, so we return 2 times 102, 204. But back here, the value of I is still 101. Now, in some languages, if I called the function and I passed the argument I with a value of 101, and in my function I said arg equals arg plus 1, when I come back here, I would find that I had been incremented to 102. That does not happen in C. That happens if we're in a language where we pass by reference or by address. But in C, we always pass by value, and so the function cannot change the value of the thing that we pass. So that's important to keep in mind. Now, if I wanted to, you know, change the value of arg, I could return it as a function value, or I can start thinking about passing pointers. So we'll get to pointers in a little bit. Let's just take a look at multiple arguments. So let's make an add function. And our add function is just going to add x, y, and z. And I can just say, you know, answer equals add, and I don't know, what number should we add? Let's add 5, 7, and 8. And then let's print out what the answer is that comes back from our add function. So my add function is going to take these three arguments, add them together, and return that as the function value. So let's save that. Let's compile it and run it, and it tells me answer is 20. Well, 5 and 7 is 12, plus 8 is 20. So it's, you know, a function that's adding three numbers together. Success. And it doesn't really matter what I do in here, right? I could say, you know, integer sum equals x, sum equals sum plus z, sum equals sum plus y, and then I could say return sum. Doesn't make any difference. Well, except that I misspelled sum. Right? Doesn't make any difference. The only thing that matters is what's the value that's returned in this return statement. And you know, this is just a longer way of calculating the sum of those three arguments. So the only thing that I know when I come back from that function call is what was the value in the parentheses of the return statement. All right, so that's the basic mechanism for calling a function, returning a function. All right, let's talk about prototyping a function. So this is something that will come up a lot. Function prototypes. So let me take my main program and let me put it up here in the beginning, because a lot of times we like putting our main program first and then putting the functions that we're calling afterwards. And when I do that and I try to compile, I get a warning. It says implicit declaration of function add. And it's pointing to line 5 of my code. So if I go to line 5, right, which is right here, it's the statement where I'm calling add, where I'm getting the warning. Always pay attention to warnings, right? If you're absolutely certain what the warning is and that it's not important and this is not something you're turning in for a grade, you can ignore warnings. But any other case, pay attention to your warnings and make sure you clean them up, make them go away. All right, so what's the problem here? I'm calling a function add. At this point in my program, I have not told the compiler anything about the function add. The first time the compiler hears about it is when I'm calling it. And that's kind of a harsh situation for the compiler to deal with. Because yeah, I'm passing three numbers, but you know, honestly, are these numbers integers? Are they floating point numbers? Are they double precision floating point numbers? Not really sure, right? Because I could write the number 5 and I could mean the floating point number 5. So it will make an inference and probably assume that these are integers. And I'm taking the result of this function and I'm storing it in a variable answer, which is declared to be an int. So it's going to assume this function is supposed to return an int. But it would be nice if it actually knew that, if I had actually told it, this takes 3 integers and it returns an integer. It doesn't actually see the definition of the function until we get down here. So what we can do is we can make what's called a function prototype, right? And a function prototype is basically something which just tells the compiler, hey, you're going to see me talking about a function named add. This is what add looks like. And so our function prototype looks like this. Right? Integer add, parentheses, int, int, int. All you have to tell it is what type of argument you're giving and what type of return value. So that's the function prototype for the add function. And as long as I do that, I can compile and I don't get that warning error message. All right, so so prototyping your functions is useful, and the basic idea of this is imagine you're building a house, right? And your job is to build the kitchen, and your particular job is to build the countertops, right? And one of the counters is going to hold a sink. And so you're designing, you know, what the counters are going to look like, what the wood is going to look like, and so on. And you get to the part where the sink's going to go. Now, if you actually had the actual sink in hand, you could measure it and figure out, you know, how deep the space needs to be underneath and how wide the hole needs to be on top, and so on and so forth. But if you don't have the actual sink in hand, you can still build the countertop if you know enough information about the sink. If someone tells you, okay, here's the dimensions of the sink, here's an outline of the top, here's how deep it goes down, you could use that information, design the top, and then eventually when the sink shows up, you just pop it in place, right? That's basically what's happening here. We're trying to build this main program. We're going to use this sink, this component called add. And if we don't know anything about it, if we've never seen a description of add, we don't know exactly what that function is going to be like. How many arguments does it really want? What are the types of those arguments? What type of thing does it return? So this is like, you know, a description of the sink. It's like, okay, I'm not going to actually give you the sink. I'm not actually handing you the function yet, but I'm telling you when you see this function, it's going to take 3 integers as arguments, and it's going to return 1 integer as a function value. Okay, why is that useful? Why not just, you know, put our function before our main program? Well, here's what we can do. We can take our main program and we can start to split it up. We could take the add function and get rid of it, and we could make a functions file that just contains our add function. So what have I got? I've got a main.c and I've got a funds.c. Main.c just calls the add function, prints out the answer. And I don't have any code in here that says, you know, what the add function looks like, but I do have a function prototype so that the compiler is able to deal with this function it hasn't seen yet. And then this funds.c file, that contains the actual add function, but not the main program. So if I want to compile this, I could say gcc-o main. Well, if I just say main.c, it's going to tell me, hey, there's an undefined reference to add. Right? My main program, main.c, tries to call add, but it doesn't know where that is. And if I just try to compile funds.c, I'm going to get a different error, which is undefined reference to main. In other words, there's no main program. But if I compile both of these together, I get a good executable program, which does, you know, what I'm hoping it will do. So being able to use these function prototypes is important because it will let us take our program and break it into pieces. And when we're modularizing, when we're trying to break big problems into smaller problems, this is exactly what we want to do. We want to write a file containing just our main program, for example. And the only thing we're going to put in here are the statements that make our main program, you know, do whatever algorithm we came up with. So the C version of our pseudocode for our main program. But we're probably going to use a lot of other functions. And for example, the printf function is not, you know, part of this file. So it's in a library of functions that are included for us, but it still needs to be prototyped. And the prototyping happens in stdio.h. And if we search this for printf, we'll find the prototype for it right here. So it says this is an external function. It returns an integer. It's called printf. It takes a character array, and then this ... is something called varargs, which says it can take, you know, 0 or more additional arguments. And there's the semicolon at the end. And the semicolon at the end is the thing that makes this a function prototype. as opposed to the beginning of the declaration of an actual function. So we've been using function prototypes all along, but they were written for us inside this standard io.h file. But when we write our own functions, like this add function in a separate file, we need to prototype it wherever we're going to use it. By the way, you might notice in here I did not include standard io.h. Why? Because none of my function calls in here have anything to do with standard io.h. In fact, I'm not calling any functions. I'm doing an assignment, I'm doing some addition, I'm saying return. None of that needs a function prototype. But if I were to call square root or print or fgets or something, then I'd need to include standard io.h, math.h, whatever. Alright, so that's our basic setup with functions. Alright, let's look at this business of pass by value and see how we can live with that if in fact we do want to change the value of an argument. Because this return, only lets us return one thing, right? We can return an integer in this case. And later on in winter, we'll talk about structures, and we can return a lot of information through a structure. But for now, we can basically return one thing. So suppose we wanted a function that would actually change the value of an argument. For example, suppose we want a function that actually sets the first argument equal to the sum of all three arguments. Or let's just set it equal to the sum of the second and third arguments. Right? So my goal is to take three arguments, add the first two, and set x equal to the third. And I'm going to change my function to void because I'm not going to use the function return value for anything. Right? I'm just going to take the second and third arguments, add them, set the first argument equal to that. So I can just say x equals y plus z. And I can say return without any arguments. But that's actually optional. If I don't say return and I hit the curly bracket, the function will return at that point. So, but putting return is nice because when you're reading the code, that's where you exit the function. So I take in two arguments, add them, store it in the first argument. And so let's use this. So I'm going to change the prototype for my function. Take three integers and return nothing. And so let me try this. So I'll say add x 5, 6. And we're hoping that our function add is going to take 5 and 6, add them together, set x equal to 11. And so we'll print out the value of x after we make this call. So we can compile this, and then when we run this, x turns out to be equal to 0. Alright, so let me bring our function inside our file. And if you're wondering how I did that, I went down to the bottom of the file by hitting a G, and then I said :r space and the name of the file I want to read, and that pulls the file in right there. Then I'm going to :w to write it, and now I can gcc-o main.c and then run main. Alright, so I'm doing this so I can look at the function in the same file as the main program. Alright, so the problem here is that C is passed by value. When I say add and I put in x here, it looks at the current value of x, which guess what happens to be 0, and it passes that number 0 down here. And in my add function, I set this local variable x equal to 0, and here I set that local variable x equal to 11. It has nothing to do with this variable x. Totally separate variable. This is a local variable in main. This is a local variable inside the add function. The only thing they have to do with each other is that when the add function starts, the value of this x is the same as the value of that x. That's what pass by value means. But when I change x, I'm changing a totally different variable. And when I come back here and I try to print the value of x, I'm printing the value of this variable, which, guess what, hasn't changed. So how do we make this work? So we can pass the address of x, And down here I can say that x is a pointer to an integer. And down here I can say the thing that x points to should be set equal to x plus y. And that's going to change the value up here. So yeah, I'm still passing by value, but the value I'm passing is the address of x, right? I'm passing the place in memory where x is stored. So if x is stored at box 112, right, there's x sitting inside there. This is going to say add parentheses 112, comma 5, comma 6. And down here I take 5 and 6 and add it, I get 11. And star x, remember, means look at the value of x. That's, you know, whatever happens to be there. In this case, the value of x is the thing I passed, 112, right? The number of the box where x is stored in my main program. The star x equals means go to box 112, open it up. That's where we're going to put the 11. So when we return and we come back up here and we try to print the value of x, we're going to go to whatever box x is stored in, which is 112. When we open up that box, we're going to see the number 11 in there. So it's technically still passing by value, but we're pretending that we're passing by reference. We're passing the address of x. We're using the address of x to change this variable up here. So if I compile this and I run it, well, I can't compile it yet because I've got a problem with my function prototype. How do I know that? Look at the first error you get when you compile and you get multiple errors. Look at the very first error. If they scroll off your screen, scroll back and find the first error. In this case, it's at line 8, and if I do an H-Shift-G, I can see it's right here where I'm calling the add function. Passing argument of 1 of add makes integer from pointer without a cast, right? And it spells it out a little further. Expected int, but argument is of type int star. In other words, I'm passing a pointer to an integer, but it expected an int at line 3 of main. What's line 3 of main? Hey, it's my function prototype. And I told the compiler, when you see the add function, this first number is going to be an int. But when I actually use the add function, my first argument is not an int, it's a pointer to an int. So my prototype doesn't match the way that I'm using the function. So the only problem here is I need to declare that first argument to be an int star. And now if I compile it, it'll compile fine. And when I run it, sure enough, x is equal to 11. So that's why we sometimes pass ampersand variable name to a function. For example, when we use scanf or scanf, and you want to, scan something with a %d and get the value, you pass an ampersand of the variable name. That's exactly the reason why. All right, last thing I want to talk about is, back to arrays. We looked at arrays when we looked at pointers, and we noted that arrays are really pointers. An array of integers is really a pointer to one integer, which is at the beginning of a set of integers stored somewhere in memory. So let's modify our main program. I'm going to declare an array of 5 integers, and I'm going to initialize it, using the curly bracket approach of just listing the values in here. So 2, 4, 6, 8, 10. Those are the 5 values I'm storing in my array. And I want to make a function sum which adds up those 5 values. And I'm going to call sum, pass it that array, and get the results back in x. And then I'm going to print out the value of x. So my sum function, I'm going to declare it not to take an integer of 5 elements. I'm going to declare it to take a pointer to an integer, because that's what an array is. It's a pointer to whatever kind of object is in the array. So an array of integers is really a pointer to an int, and so I'm going to declare it as such. But once I've declared it as a pointer to an int, I can legally say arg bracket index to access an element of that array. So my function is pretty simple. I just take the 5 elements of the array, add them together. I'm storing that in sum, and then I'm going to return sum. And up here, x should be set equal to the sum of those 5 elements. So let me save that. Let me compile it, and let me run it. And sure enough, x is equal to 30. And if you add these up, 2 and 4 and 6 is 12, plus 8 is 20, plus 10 is 30. And you know, you always want to test your data, your code pretty thoroughly. So I could make you know, another array of data, and I could make a third array. Like that. And then I could set x equal to sum of data 2 and print out the value of that, and set x equal to sum of data 3 and print out the value. So I'm going to call my function 3 times. The first time I'm going to use this array, which should give me back a 30. The second time I'll use this array, which should give me back a, I think the number 3, and then this array, which I think will give me back a 25. And so, you know, I've got one function, but I'm calling it 3 different times, and I'm going to have to get rid of these int keywords here. So let's try that. Let's compile it, and let's run it, and yeah, x is equal to 3, x is equal to 30, x is equal to 25. If I thought, you know, there was some case that might break this, and you always want to look for edge cases when you're writing functions. For example, if I thought that, you know, negative numbers might be a problem, right, I would make sure I had a case with negative numbers. If I thought there might be a case where having a sum of 0 would be a problem, I might do something like this. Right? And I know that the sum of these numbers is going to be 0, and I could compile and test, and yeah, x equals 0, no problem, it didn't break anything. So, you know, depending on the function you're writing, you want to be thinking about, you know, the algorithm that you use. Granted, this is a pretty simple algorithm, but for a more complex algorithm, right, what might break it? What assumptions am I making that could be violated and might change what my program does? You always want to try to find those edge cases and exercise your code with it. All right, so what's the obvious problem with this? It's this number 5, right? I'm always passing an array of 5 elements. What if I wanted to pass an array of 6 elements, right? Well, my function is written to only add 5 elements. And remember this kind of quirk of C. If you have an array, there's nothing about the array that tells you how many elements are in the array, because the array is just the location in memory where the first element is stored. There's no inherent length to an array. So to make this better, I might want to actually do something like pass an array of integers and also pass an integer saying how many things are in that array. And so I would, you know, say sum data comma 5, and instead of writing one statement like this, I might do something like, you know, a for loop that would add to a running sum. And then I have a much more general purpose function. But the point here is, you know, passing arrays, we can just pass it with the name of the array, and in the receiving function, we declare that argument as a pointer. Two-dimensional arrays, different story, but we'll avoid those for now. All right, so that's the basic overview of functions in C.